and go from current slide. And we are now recording, and the only two announcements I know about, there may be others. College transfer day is coming up the second week in February, February 12th on the Birmingham West Campus in the B building, academic building, from 9:30 to 11:30. They'll be all up and down the hallway there on the tables. And then on Thursday on this campus, February 13th from 9:30 to 11:30, this building, Building A, but it will be, they say the campus cafeteria. I think what they mean is the faculty staff dining room, which is right next to the cafeteria. And that will be 12th and 13th of February. And then this is that research program for undergraduates, the Center for Power Optimization of Electrothermal Systems, POETS. Okay, and that will be at one of three universities, Arkansas, Illinois, and Howard University. 10-week program. They pay you $5,000 to participate. You learn a tremendous amount. They house you for free. I think that includes feeding you for free, and they include airfare one trip there and back, so round trip one. Okay, and the deadline for that was the 15th of February. And I've got this information. You're certainly welcome to look at. Should be a great opportunity. You learn a lot. Okay. Any questions on anything we've done so far? Okay. Now, where we left off last time, we had talked about remember we had done solving systems of equations, and we had, what did they call them? Equation operations, I believe is how we would have said it. Yeah, my eyes are giving me. Operations that produce equivalent systems of equations. In matrices, we are talking about elementary row operations. But remember, each row can represent an equation. So it's sort of the same type deal. Remember what those three were? Interchanging any two rows, multiplying any row by a non-zero constant. I like to say multiplying or dividing by a non-zero constant, and adding a multiple of one row to another row. Those are the three allowed operations that give you equivalent matrices. So, we're getting ready for example 2, or at least that's where I left off, right? Okay. So, example 2. Here's an equation. Let me get my pen set up. Okay. Here's a matrix. 0, 1, 3, 4, -1, 2, 0, 3, 2, -3, 4, 1. I'm not going to quite do it the way the book does it. We will do it the way the book does it, but I'm not going to do it that method or procedure. Okay. What would be your ideal situation for that matrix? What would you want to be true about it? Yes, they have the first non-zero entry. The first entry in the first row, first column, you want that to be a 1. You don't have it. Is there an elementary row operation that would at least move you in that direction? Okay. Now, if I'm hearing you right, what you're saying would be a legitimate thing to do. Subtract row 2 from row 1. Okay? That actually would work, and it would probably come out okay. That's not the way the book is approaching it, but that would. So row 1 minus row 2 would be the new row 1. The only thing that's a little problematic there is usually, make sure I say this right, we usually, though it's still a legitimate thing to do, we usually use a row and add or subtract something of the other to change this row, okay? We most of the time don't do the other, though I think it is a legitimate thing to do. What the book is suggesting, which is usually a safer route, but I think what you said would be fine too. In fact, we can do this and see if we get the same answer. Are we going to carry it all the way through? No, we're not. They were suggesting just exchanging these two rows. Doesn't give you a 1 up here, but it gives you a minus 1, and then it's really easy to change that to 1 by negating the term up there. So that's what they were suggesting. Now, I wish we had time. I would check and see if both of those are equivalent. I think they are. And I think you could do what you said, but what the book wants you to do is the other. So what would, so I'm going to do, according to the book, row 1 and row 2 interchange. So what would be that, the result of that row operation? Negative 1, 2, 0, 3. And the last one would be, yeah, because you didn't do a thing to that one. Okay. Now, the other advantage of doing it in this system this way, it's real easy to make that a 1, that top one. Just negate everything on that row. And then it would be really easy to get this to become 0. In fact, I would do that before I negate it. 2 times that one plus this one like that. Okay, so that makes that easy. And you already got the next one exactly what you want. First non-zero entry in the second column will be a 1. So that was sort of the advantage of doing that. If you did it the way you said, and subtract row 2 from row 1, sure you would get that, but you would still have this as a row 2, and then you'd still have to go back and do some other things. So I think this might be fewer operations, and that's what's going to drive a lot of this. And here's why. Most of the time, you're not going to do these things. You're going to set up computer programs to do them. And CPU time is what costs. So if you can minimize the number of operations, then you minimize CPU time. And though it doesn't seem like a lot for huge systems, that can add up. Okay, so that's what they wanted you to do. Okay, let's do the B one here. Okay, 2, negative 4, 6, negative 2, 1, 3, minus 3, 0, and 5 minus 2, 1, 2. Now, if I'm getting any of these numbers wrong, let me know, because I'm not seeing well without the glasses on. Okay. Now, in this one, you have 2 fairly equivalent things to do. What would be 2 things that you would consider doing here?
trying to do again?
Okay, what's the optimal situation? What do you want to be the first? What do you want this to look at the next step? What's that first desirable feature you want this to have? Same as before. Your 1 in the upper left corner. Okay? There's two ways you can get to there from here. How?
You can either swap them or multiply the first one by 1 half.
Exactly. And they want you to do the multiple thing first. And I like that as an idea anyway, because anytime I can make my numbers smaller, there's going to be fewer chances for me to make errors. Okay? So that would be my choice here too. Or, like you said, you could flip those two rows. So let's do what you said. Only I'm going to phrase it a little different. Oh, I'll phrase it the same way. 1 half row 1 is the new row 1. Okay? So what would that produce then?
1, 2, 3,
Perfect. And then everything else stays the same. You haven't done anything else to any other row. Now, to me, this is the biggest problem with matrices, is you just wind up writing a lot of numbers over and over and over. It's a pain in the neck, but you have to be careful and make sure you don't introduce any errors you don't want in there, and any error is unwanted. Okay. Now, here's another matrix. 1, 2, minus 4, 3, 0, 3, negative 2, negative 1, and 2, 1, 5, negative 2. Okay. Now, what's the number one thing that you want to happen here?
bottom left one would be 0.
Exactly. This is exactly like you want it. That's exactly like you want it. So the next one is that becomes a 0. How do you make that happen?
Would you multiply the first one by 2 and subtract it?
And subtract it. Or even easier, I think, is multiply that by negative 2 and add it. When I start subtracting, then I get the signs right. Adding, most of the time I'll get the signs right. All right, we just doubled the class size and wound up with perfect attendance, okay, at the same time. So, way to go. All right. So, what we're doing are, I think you were here when we were doing system operations to get equivalent systems of equations. Now we're moving to matrices, which I don't know if you followed enough to know what matrix is. Those are just arrays of numbers. We're using the same elementary row operations now rather than equation operations. And that is swapping any two rows like we did here. That's legitimate. Dividing or multiplying any row by a non-zero number, which is what we did here. Divided this by 2, every element in the row. And the last one here, what we want is a 1 here, 0 there, 0 there. To get this to be a 0, what did we say we did?
Multiply the 1 by negative 2.
Negative 2 and add to the third. Okay? So here's how I document that. I'm doing it to the third row, so I'm going to negative 2 times row 1 plus row 3 is the new row 3. Okay? So do it to it. In other words, 1 and 2 stay the same, so like we were saying before, you just wind up copying a lot. 1, 2, negative 4, 3. Make sure you copy carefully. 0, 3, negative 2, negative 1. I hope I wrote them right. Okay? Now what's your new row 3? 0. Negative 3. 13. -8. Okay. Now, I'm sort of glad we don't have to do much more to this one, but if we did, what would be your next move?
Add the first and third row together.
Say that one more time.
Add the first and third row together.
Okay.
Well, so I know when we had like the systems, the next step would be to find like X or Y. So what do we do next?
Okay, yeah, okay, here's what we're looking for. We wanted a 1 there, we had it, they gave it to us. We wanted a 0 there, we had it, they gave it to us. We wanted 0 here, we just did it. The next thing we usually want to happen is to have a 1 there. So how we would get that usually would be divided by 3. That gives you fractions there, negative fractions. Okay. Before I did that, what you would want after that was this to become a 0. Well, hey, let's go and make that be a 0 now, because that's going to be easy. That would be add these two rows together, 0, 0, 11, and minus 10. No, minus 9. So I said, I'm glad we're not doing anything else with this, and this is coming out really nasty numbers. But then after doing that, then you want the 1 there. Because if you can look ahead a step or two and see an easier way to do something rather than making that a 1 and then have to multiply by 3 and doing this, introducing more possibilities for errors, minimize your errors. When you're programming this, you won't have, you don't have to run through all that. But that's a computer doing it, not you. So if you can see a step that would make it easier to do ahead of time, do. Just like you did there. I think your first step there was a pretty good one. I liked it better than what they said. But looking ahead, it probably was not going to be much better in the long run. But I couldn't tell that for sure. But so anyway, the purpose of this is just to get you used to the elementary row operations. Now, back in section 1.1, any questions so far? Got it? Back in section 1.1 in example 7, you use Gaussian elimination with back substitution to solve a system of linear equations. This next example demonstrates the matrix version of that Gaussian elimination. The two methods are essentially the same. The basic difference is that with matrices, you don't need to keep writing the variables. It's already bad that you have to write so many numbers over and over, but you don't need to write variables over and over. So that's the main advantage of matrices, to eliminate that. So let's go to example 3. Any questions for our RACs? All right, here's your linear system. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Now, if you feel like some of these numbers look familiar, I think they use many times the same things over and over again. But try to do it as first. Let's write the associated, what they say, augmented matrix. What would that be? One, negative 2, 3, 9. Next. Yep. -4. Next. Okay. Now, main thing that did for you, eliminates you having to write that variables. Okay? Numbers you still have to write. Okay. Now, what's your optimum thing you want to exist here to begin with? 1 in the upper left, you got it. This is fantastic. Don't have to do a thing together. Next. 0 below it. And that's going to be pretty easy. How do we make that happen? Okay, row 2 plus row 1 is the new row 2. Okay? Now, anytime you're using a row, and that's why I was trying to say before, whatever that row you're using, which is the first row, and by the way, most of the time you're using the row with that leading one or the element that you're trying to deal with. So we're using that leading one, so that's the one you list twice. When you're using a row, you're not messing with the row. So that stays the same. 1, -2, 3, 9. Okay, what's your new row 2? 0, 1, 3, 5. Okay. Now, you don't need to write the other one down. You didn't use it, you weren't using it. Let's go on and do what we want to, to do with that one. What do we want the next thing to happen? If you want a 0 below that, how do you get that 2 to become a 0? By what? Okay. -2, row 1, plus row 3 is the new row 3. And I actually said this backwards. This should have been row 1. I think you said it this way. Plus row 2 is a new row 2. Because the second one, I get cross off. It doesn't really matter on that one, but this one, that makes a little more sense. Okay? So do it to it. Zero. Yeah, wait. Okay. -1. Next. Second. -1 again. Next. -1 again. You're stuck on -1s, aren't you? Okay. Now, what do we want to happen next? Or to be the situation next? You've got the first non-zero entry in row 1 to be a 1. 0 is below it. Done. What you want next? First non-zero entry in row 2 to be a 1. And guess what? It's already there. What do you want to happen next? 0 is below it. So how do you get that to happen? Row 2 plus row 3 is the new row 3. Okay? So you're not using row 1. You already got its leading one. Leave it alone. 1, -2, 3, 9. Row 2 you're using, so leave it alone. 0, 1, 3, 5. What's your new row 3? Got it. What's the next thing you want to happen? You wanted a 1 there, you got it. 0 is below it, you got it. Leading non-zero entry here, a 1, you got it. 0 below it, you got it. Next. The 2 to become a 1. How do you make that happen? Divide by what? Multiply by 1/2 or divide by 2, either one. So row 3 divided by 2 is the new row 3. Okay? So that becomes, you're not messing with the first row, write it down. 1, -2, 3, 9, 0, 1, 3, 5, and what? 0, 0, 1, 2. Okay. That is what we call a row echelon form. That's Gaussian elimination. That's what you do. Now, with Gaussian elimination, what's the next phrase? If you do Gaussian elimination, you back substitute. What does this tell you? Especially that third row, what does it tell you? Given that this was your original system of equations, this is z is equal to 2. Perfect. Because these numbers represent the coefficients of, and the columns represent the variables. So that would be z equal 2. So that's what you got. Now where do you go from there? Yes?
So every time you make decision, you want to then 1, 0, 0, then 1 in the second row, in the second, and then 1.
0 under it, and then the first nominal is 0, 0, 0, 1. Yeah. Now, they all won't come out pretty and nice like this. But if they do, this understanding that all this came from this system of equations. We took out the variables from the very first step. Now we put them back in. But we put them in judiciously. Just here, z is equal to 2. Now here, put them back in, and what does that represent? Y plus 3z is equal to 5. But we know what z is. So that would be y plus 3 times 2 is equal to 5. That would be y plus 6 equal 5. That would be y is equal to, say again? -1. Done. Okay? Guess what? That's called back substitution. You're substituting going backwards with it. Okay? Next. X minus 2y plus 3z equal 9. That was our first equation right up there. Okay? And what do we do now? Okay. X minus 2 times -1 plus 3 times 2 equal 9. Okay, I'm going to have to come down here and finish that. X oh my, this, I have a lousy plug connection here, and this outlet in here, once it goes too long, it starts running down my battery, and my battery's already low from the weekend. Okay, now sorry about that. Okay, I think that's charging a little bit better now. Sorry, system. Okay, so we have x minus 2 times -1 is plus 2 plus 6. Okay, what does that give us? X equal 1. Let's see if that worked. 1 plus 2, when you plug in a -1 for y, plus 6. Sure enough, that's equal to 9, right? Okay, let's do the next one. -1 plus 3 times -1 would be -3 is equal to -4. That checks. And then the third one would be 2 times 1 is 2, minus 5 times that would be plus 5, and plus 10, sure enough, is 17. Yep, that checks. And every system of equation is either going to have how many solutions? One solution, or an infinite number of solutions, or no solutions. We found the one and only one. Okay, good deal. and we wound up with 1, -1, 2. Now, I said it ahead of time. This is what we call row echelon form. Here's the definition of row echelon form. The leading non-zero entry in every row is a 1. Secondly, the 1 step from the first row to the subsequent rows, they always move at least one place to the right. Okay? Oh, I left off one. Any row of zeros is moved to the bottom. So those are the 3 rules to give you row echelon form. Any row of all zeros gets moved to the bottom. Secondly, leading non-zero entry in each row is a 1. And thirdly, the 1s are stepping to the right in the row above. Okay. Now, they won't always step just 1. They may step 2 or 3. But that's going to be the rule. So a matrix, I guess I ought to write this down since y'all don't have books yet, do you? You have an e-book already? You do. Do you? Oh, you do. Okay. Can you read it on your phone? Or is it too small? Anyway, I'll say again what I just said. Okay? A matrix in row echelon form has these properties. Any rows consisting entirely of zeros occur at the bottom of the matrix. Make sure that happens first. Wind up with a row of zeros, move it to the bottom. For each row that does not consist entirely of zeros, the first non-zero entry is a 1. The name for that is the leading 1. I'll start calling that from now on. Leading 1. Okay? Number 3. For 2 consecutive non-zero rows, the leading 1 in the higher row is always further to the left than the leading 1 in the next row. Okay? For every row that is not all zeros. Now, that's row echelon form. Here's one more statement. A matrix in row echelon form can be written in reduced row echelon form when every column that has a leading 1 has zeros above it as well as below it. Now, if you don't have a leading 1 in a column, you can't do a thing with it. But if you do have a leading 1, like the ones we just did, sorry, I erased now, I shouldn't have. It wound up a 1, -2, 3, 9, 0, 1, 3, 5, 0, 0, 1, 2. That's row echelon form. To get it in reduced row echelon form, that 1 in the second row would need a 0 above it. The 1 in the third row would need 2 zeros above it. Okay? Then that would be in reduced row echelon form. Okay. So let's do row echelon form. What they're asking here is determine whether or not each matrix is in row echelon form. If it is, determine whether the matrix is also in reduced row echelon form. So that's what you're doing. First question, is it in row echelon form? Second question, if it is, then is it also in reduced row echelon form? Here's the first one. 1, 2, -1, 4, 0, 1, 0, 3, 0, 0, 1, -2. Is that in row echelon form? Say again? Yes, it is. Find those leading 1s, and everything below a leading 1 is 0. Okay? And the leading 1s go left to right. Okay? And as you go top to bottom, and there's all rows consisting totally of zeros are on the bottom. Okay. Now, here's the B. 1, 2, -1, 2. 0, 0, 0, 0. 0, 1, 2, -4. Is that in row echelon form? Oh, wait. Go back to the first one. Is that also in reduced row echelon form? The first one. Not quite. To be reduced row echelon form, that would have to be a 0, that would have to be a 0. You need every leading one would have zeros below it and above it. These two keep that from being reduced row echelon. It is row echelon form, but not reduced. There's a second one, row echelon form. Why not? Row of all zeros cannot be in the middle, it has to be at the bottom. So that is not. If you were to flip those two, would it be in row echelon form? But the second and the third.
Is that 0?
That's a 0. Sorry. That was 0.
Yes.
No, it would be row echelon form. Would it be reduced row echelon form? No. So that's 2 again. Okay.
I thought,
Yeah.
row echelon form meaning the one in the bottom of the third or two.
Okay. No, that's not a requirement.
Oh, okay.
It's every non-zero row, the leading non-zero entry has to be a leading, has to be a 1. So if you flip those two, this is the leading non-zero entry is a 1. If you flip these two, the leading non-zero entry was a 1. And then you have a row of all zeros at the bottom. And they're stepping down. That wouldn't be, if that represented a system of equations, you would have an infinite number of equations. You might even have no solution. It would not be a unique solution. Guaranteed. Okay, the third one. These are fun to write, aren't they? 1, -5, 2, -1, 3. 0, 0, 1, 3, -2. 0, 0, 0, 1, 4. Fourth line, fourth row, 0, 0, 0, 0, 1. All right. First question, is it in row echelon form? Yes, it is. First non-zero entry in each row is a 1, and the 1 step from right to left, and you have no rows of all zeros. If you did, they have to be at the bottom. Now, this is a legitimate matrix. Remember, matrices don't have to represent systems of equations. So far, that's what they've been doing. If this did represent a system of equations with 4 variables, 4 equations, what would be your solution to this one? How many solutions would you have?
I mean,
None. Because this 0 can't equal 1. Huh?
With 0 can equal.
Yeah, if this did represent 4 equations with 4 unknowns, x1, x2, x3, and x4, and those are your constants, then this last row would say 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1. Not going to happen. Okay. But remember, this doesn't have to represent a system of equations. This is a matrix, which it is. It is in row echelon form. Is it in reduced row echelon form? Why not? Yeah, because that 2, that 3, that -1, and all those numbers would have to be zeros. This not. Okay. Number D. Okay. 1, 0, 0, -1. 0, 1, 0, 2. 0, 0, 1, 3. And 0, 0, 0, 0. Okay. Is that in row echelon form? Yes, it is. Row of all zeros is at the bottom. Leading entry in any non-zero row is a 1, and the 1s are stepping from upper left to lower right. Okay. Is it in reduced row echelon? Why not?
Is the 3 next to the
Say again?
The 3 on the third row, sum is 0.
Okay, it doesn't have to be. Remember, to be reduced row echelon form, those leading ones just need zeros below them and above them. This doesn't have a leading
Well,
one.
the negative 1 has a.
Okay, but this doesn't have a leading one. If that was a 1 down here, yeah, these would have to be zeros. That's a 0 down here. Okay? It's the leading ones have to have zeros above them. That's all there to be reduced row echelon form. Now, what this does represent, if you did have any system of equations with 3 variables, but you had 4 equations, okay, then this would be, you have found your solution. One and only one solution. Z equals 3, y equals 2, x equals -1. That's the advantage of reduced row echelon form. You don't have to do back substitution. This one you would have had to do back substitution. Well, this one wouldn't have worked anyway. That one you wouldn't have had to, you would have to do back substitution because this would have been z equal -2, y equal 3, and then you'd have to plug in those values here to find out what your x is. When you have reduced row echelon form, then, and this does represent a system of equations, read off your answer. X equal -1, y is equal to 2, z is equal to 3. Okay. That's the advantage of reduced row echelon form. It makes that next step easy. Now, the other thing is what we're going to be doing, if not next, close to next. And we'll see that. Okay, that gives us those 4. Let's go to number 5. I'm going to erase this. Is that okay? Okay. The E here. 1, 2, -3, 4. 0, 2, 1, -1. 0, 0, 1, -3. Is that in row echelon form? Why not?
The second row's leading coefficient is 2.
Is a 2. Leading non-zero entry is a 2, not a 1. Now, to get this to be row echelon form, just divide that second row by 2. That was 0, 1, 1/2, -1/2. That would then be in row echelon form. Would it be in reduced row echelon form? No, because the numbers above those leading ones would not be. So it's not row echelon, nor would it be, of course, reduced row echelon. All right, and here's another one. 0, 1, 0, 5, 0, 0, 1, 3, and 0, 0, 0, 0. Okay. First question, is it in row echelon form?
Do you have to have a 1 in the top right? Or
No, you don't. That's the deal. This, I don't know what that represents, but it sure isn't a very good system of equations. But it is in row echelon form. Because what's required is that all non-zero rows must be at the bottom. And then for any all zero rows must be at the bottom. For any non-zero row, all that's required is the first non-zero entry to be a 1 for every row, and that the 1 step from upper left to lower right. This fits the thing. That is in row echelon form. Is it in reduced row echelon form? Yes, it is, because not only do those leading ones have zeros below them, they have zeros above them. That 1 does. Now, as a system of equation, I don't know what to make out of this. That would be z is equal to 3 and y is equal to 5, and it doesn't matter what x is. Okay, so this would be something in the YZ plane with no X variation at all. Okay. I think. Okay. You don't need to know that. Okay. So let's make sure they got them right. The matrices in A, C, D, and F, A, C, D, and F were all row echelon forms. The matrices in D and F were in reduced row echelon form. And then it goes into the ones that Y matrix in B is not in row echelon form because the row of zeros does not occur at the bottom, and E not in row echelon form because the first non-zero entry in row 2 is not a 1. So we've done that. All right. Now, it seems like we've already done this, but let's, okay, you both have your books, or e-books, right? Gaussian elimination with back substitution. Okay, we've done it, but let's review it. First, write the augmented matrix in as a system of linear equations. Okay. Write the augmented matrix of the system of linear equations. In other words, write the coefficients, and then the last column will be the constants. Any variable missing, be sure you put a 0. Number 2, use elementary row operations to rewrite the matrix in row echelon form. Now this is Gauss elimination. Then 3, write the system of linear equations corresponding to the matrix in row echelon form, and then back substitute to find your solution. Okay. Now, my eyes are giving me fits because I don't have my glasses. They do have a little hint here. Gaussian elimination with back substitution works well for solving systems of linear equations by hand or with a computer. For this algorithm, the order in which you perform the elementary row operations is important. Operate from left to right by columns, using elementary row operations to obtain zeros for all entries directly below the leading ones. So you really should have said, get the leading ones first, then zeros below it. Now, the linear algebra applied is talking about GPS systems. Now, the GPS is a network of 24 satellites originally developed by the U.S. military as a navigational tool. Today, the GPS technology is used in a wide variety of civilian package delivery, farming, mining, surveying, construction, banking. They just go on and on and on. It uses linear algebra to do what it does. I didn't know we only had 24 satellites up there, before I read this. Now, they use some terminology in there. It just, I think, is a fun thing to read. But let me just tell you this. I grew up in Georgia on a farm. My dad was a farmer. When he was approaching, I don't think old farmers really retire, but when he was getting close to cutting back a lot, my younger brother wanted to farm full time, but he couldn't afford to, not with his lifestyle and his wife's desired lifestyle as well. So he worked full time and farmed on the side. My older brother at some point had moved back to the farm, so they worked together pretty much. But then after my dad died, he split the farm up into 4 pieces, but left it with my mom having lifetime rights to it. And that worked well for several years, but then when she died, they continued just like we had been doing. And then when my younger brother decided he wanted to farm full-time, so he retired early so he could. It took him 1 year to see he was losing money because when he had been working, he was supplementing the farm with his income. He had a good income at work, so he was keeping it afloat. Once he quit working, he didn't have that source, so he was using up his retirement. And he decided he didn't want to do that anymore. So we went from being small grain, beef cattle, basically operation with some trees. When they needed thinning or trimming or bad years, we cut some trees. Okay, so we decided he was just going to get out of farming. So then we need to do something to use the land, number one. And so that if you're not farming, we're going to lose the farm exemption, tax exemption. And I said, I think a tree farm is going to help us. No, it won't help us any. We looked into it, it would. So we went to do a tree farm. The big operators on that, they use GPS in planting trees. They use GPS regular farming. They have all their equipment set up on GPS so they know right where to go. I mean, everything is done GPS. Amazing, but true. So when they said farming, that's absolutely true. Surveying, construction. In fact, I was in the Navy when we first got, they called it SAT-NAV, satellite navigation system installed on the ship. Before that, we used to shoot stars at night to get our locations. We're out in the middle of the ocean. We used what they call dead reckoning, and deduced reckoning is what it was. That's how we did it. Once they got GPS, sailors quit shooting stars. They quit doing all the things they used to do to know where they were. If a foreign combatant can figure out a way to wipe out our GPS system, we're dead in the water. Literally, we don't know what to do, I think. I don't know. I'm not in there anymore, but I'm sort of glad. Okay, I'm very glad. So let's move on to example 5. That was probably way too long of talking about that. Okay. Here we have a system of equations. X sub 2 plus X sub 3. This is the example 5, top of page 17. We got plenty of time or not? Minus 2X sub 4. How much?
10 minutes.
10 minutes. We might be able to get it done. It's equal to negative 3. Second equation. X sub 1 plus 2X plus 2X sub 2 minus X sub 3 is equal to 2. Third equation. 2X sub 1 plus 4X sub 2 plus X sub 3 minus 3X sub 4 is equal to minus 2. X sub 1 minus 4X sub 2 minus 7X sub 3 minus X sub 4 is equal to minus 19. There's our system of equations. Okay? How would you go about solving it? Please don't say elimination by addition. I would not even want to try to approach that. What's your first step? Okay, and what would that be then? Zero, 1, 1, negative 2, negative 3. Next, 1, 2, negative 1, 0, 2. Next, 2, 4, 1, negative 3, negative 2, and finally 1, negative 4, negative 7, negative 1, negative 19. My writing kind of stinks, so I hope I can read it. All right. What's the first thing you want to happen? how do you want to propose making that happen?
Swap row 1, row 2.
Exactly. Let's exchange row 1 and row 2. Row 1 exchange with row 2. Okay? I'll try to fit it over here just because this is going to take a while. 1, 2, minus 1, 0, 2. I hope I wrote it right. Okay? 0, 1, 1, negative 2, negative 3. Leave the next two rows alone. 2, 4, 1, negative 3, negative 2, and 1, negative 4, negative 7, negative 1, negative 19. I hope I wrote it right. Next. Okay, and we got it, right? So next, row 3, okay? So how do we make that happen? Okay, wait, okay. Okay.
Row
3, okay. Okay. All right. I think you already said it, but let me just reiterate it. What we wanted a 1 here, now we got it. We wanted a 0 below it, we got that. Now we're going to get that to become a 0. How do we make that happen? Yeah. Negative 2, row 1, plus row 3 is the new row 3. Okay. So, next step, write down the first two rows. This is what's so redundant. 1, 2, minus 1, 0, 2. 0, 1, 1, negative 2, negative 3. Okay. All right. New row 3 is then what? 0. 0. Three. Negative 3. Negative 6, isn't it? Negative 2 times 2 is negative 4, minus 2 is negative 6, right? Okay? You may have said that. I don't hear well. What's the next thing we want to happen? Okay, that lead off with a 0 in row 4. How do we make that happen? Yeah, negative row 1 plus row 4 is the new row 4. Okay? So what would that become then? Zero. Negative 6. Negative 6. Negative 1. Whoa. Oh, wait, I can't read my writing. You're right. I thought that was a negative 1. Okay, sorry. I knew I was going to do something stupid like that. Okay, that's a negative 19 over here. I had wiped out my 9. All right. Negative 17, you're right. Okay, got it. Next.
In row 3, we'll make that 3 to 1.
Okay. And it's okay to do that now, but we also want that negative 6 right there to become 0. Usually we we do that, but it wouldn't hurt to do. In fact, I would do that also because I don't like writing so much. Okay, so we're not going to mess with row 1 at all anymore. 1, 2, negative 1, 0, 2. I hope that's right. Yeah. Okay. Row 2 we're not going to mess with anymore either. That's going to be a 0, 1, 1, negative 2, negative 3. And then, since rather than just write it down, I like your idea of doing what?
Changing row 3 to row 3. So divide, multiply by 1/3.
Yes, or divide by 3. Either one will work. And that gives you what?
0, 0, 1, negative 1, and negative 2.
Negative 2. Perfect. Next.
That one's 0.
Yeah, you want the negative 6 to become a 0. How do you make that happen?
Multiply row 1 by,
Not row 1.
multiply row 2 by 6.
Right. 6 row 2 plus row 4 is the new row 4. Right? Okay. 6 times 0 is 0 plus 0 is 0. Good deal. Okay? 6 times 1 is 6 plus a minus 6 is a 0. 6 times 1 is 6 minus 6 again is a 0. This is coming out nicely. And 6 times negative 2, what do you get there? Minus 1 is negative 13. And 6 times negative 3 is negative 18 minus 17 is seems like it's negative 35. No, 18.
Just negative 35.
Huh?
It's 35.
Okay. I'm not liking that at all. I think they get it to be a negative 39. Let me see where my error has occurred. Okay, yeah, we'll be through in shortly. At what time? Huh? It is time? Okay. Let me see where our error came up. They have that next, the previous one to be a negative 6, negative 1, negative 21. And we had, yeah, it's minus row 1. Yeah, that's the minus 21. I shouldn't listen to you. Okay. Negative 21. And here then that will be 6 times, that would be negative 18. That would be a negative 39 then, right? Agreed? Okay. And then, obviously, what's the last step?
Change the 13 to 1.
How?
Divide.
By negative 13. And that would give you a 1 and a 3. So that's not how you should do them, but that's how I did them because we're out of time. Now you've got your row echelon form. So Gauss elimination, back substitution, you start with x sub 4 is equal to 3, and back that up. X sub 3 is equal to minus 2 plus 3 is 1. x sub 2 is equal to minus 3 plus 6 will be a plus 3, no, yeah, minus 1 is 2, I think. And then x sub 1 is equal to 2 plus 1 is 3 minus 4 is minus 1, I think. Let's see if that's what we got. X of 1 equals minus 1, 2, 1, and 3. Yes. Okay. Barely finished, sorry. All right, that was example 5. We'll start next time with example 6, top of page 18. Homework exercises here include, this is a long section, isn't it? Any of the odds 1 through 5, they're all at calcchat.com. Either 7 or 9, they're both at calcchat. Any of the odds 11 through 17, they're all at calcchat. 19 to 23, they're all at calcchat. And then you can start doing any of the odds 25 to 37. Do as many of those as you feel like doing. We'll continue with those next time. Okay? By the way, is your book this one or the previous one?
This.
Sorry, I should have asked before you put away your computer.
I just had one once where it just looks weird. It looks like it's
That's all right.
No.
Okay. I'm going to be shutting this down because